Alright, today's lesson, or this video lesson, is going to be a fairly short one. We're only going to look at one application. Now, there's a lot of parts to it, but it's a special type of exponential growth. Alright, so it's a special type of exponential growth, specifically looking at money. Alright, so this is whenever you've got an investment or an account where they say continuously compounded interest. If you remember from Math 120, if you just took it, alright, we can have different compounding periods, right? We can compound monthly, daily, weekly, yearly. Well, this is sort of an example when it's compounding all the time, right? So it's continuously, all right? At every moment it's as soon as you earn money, you make money on it, all right? So compounding continuously. In those cases, the formula is exponential, and it's the same exponential function that we dealt with in the previous examples. It's just in terms of money. All right, so it's still the, again, a number e raised to RT, which has money in context in terms of money. All right, so B of t is the function, right? It's how much your future value of your investment is after however many years you have your investment for. P naught is the present value of the investment, meaning that's the initial amount. That's how much you started out with. So just like the other examples, right? It's your initial dollar amount that you invest, all right? So at times 0, it's how much you have in the account. R is the annual interest rate as a decimal, and T is always in years, because again, money grows in terms of years because we have an annual interest rate. Now, the annual interest rate, R, is the K. It's the relative percent rate at which your money is growing, right? That's what the interest rate is. And so in this application, it really is the same formula. It's just in context of money. R is the percent at which your money is growing continuously. Right, that's the K. It's the same. It behaves the same way as K, or K behaves the same way as it. All right, so I'm going to do one example since it's very, very similar to what we did in the last set of notes. All right, so again, exponential growth for continuously compounded interest. So when we invest something in, it's continuously compounded. All right, so the example we're going to look at. Suppose that we invest Suppose we invest $5,000, and it grows to $7,000 in 5 years. The interest is compounded continuously, meaning all the time, which means exponential growth. And we use this equation, which is, again, sometimes shortened as just called PERT. If you've ever heard of the PERT equation, that's what this equation is. Our A is asking us for the interest rate. Find the interest rate. All right, find R. Again, it's the same as the K for the last problem. Now, they didn't tell us the doubling time. If they told us the doubling time, we could have used that simple formula like we did it in the last example. They didn't. So this one I'm going to have to set it up and solve for my interest, my R. All right, what they did give us, though, they gave us our initial value, P naught, my initial investment, was $5,000. Then they told us a future value after 5 years, so the time is 5. Our investment grew to $7,000. All right, so that's the information I'm going to use and plug into my equation and solve for my interest rate, solve for R. Alright, so 7,000 is my future value, so that's what I set it equal to. 5,000 is my initial value, e raised to the R times 5, right? Because in 5 years, it grew to 7,000, right? That's this information. And now just solve for R. So first step, divide by the initial value. And so on this side, I'm going to simplify. I'm going to leave it 7. Right, the zeros cancel out, and I'm left with 7 divided by 5. I'll leave that exact, right? No rounding. Over here, I'm left with the e raised to the r times 5. Take the natural log of that fraction, natural log, so that the e is gone. And so over here, natural log of 7/5 equals our interest rate times 5. And then divide by your 5. Alright, so this is what you're going to plug into the calculator. Natural log of 7/5, all divided by 5. Told us to round 3 decimal places, and so my interest rate comes out to 0.067. Alright, so there's A. The answer to A, interest rate is 0.067. And so what that means is my interest rate is 6.7% compounded continuously, right? If we talk about it in terms of finance, my interest rate is 6.7%, so my money is growing by 6.7% continuously. annual interest compounded continuously. Alright, again, we're going to use the decimal version because we're going to plug it into our equation. Alright, so B, we're going to use our equation. What will the value of the investment be in 10 years? So we're looking for the future value. So I'm going to write my equation, right? I'm just going to fill in that equation with all the parts that I have. So I know my initial value, and now I know R. So my equation is the future value, B of t, equals my initial value, 5,000, e raised to my interest rate, 0.067, times any time, right? Now I can solve for any future value. We want to know what it is in 10 years, so we're going to plug 10 into that equation. Since we're talking money, all right, first of all, make sure you write units down, that it's money, it's dollars. And then I usually round it to a penny. Alright, so when you plug 10 into this equation, it should come out $9,771.19. So that's how much money will be in the account after 10 years. Alright, so that's just finding my equation, setting it up for this particular finance application. Alright, the next part. C, how fast is the investment growing initially? So how fast is looking for a speed, right? Which means derivative. Initially means time 0. So I want my derivative at time 0. So derivative first. All right, so again, we did a bunch of these last set of notes. So the derivative is always write the original expression down, right? Derivative of the e is the e, so 5,000 e raised to the 0.067 times time, but then we're not done. We got to remember to multiply by the inside, which means multiply by that decimal 0.067. And again, it should make sense. Derivative is how fast your money's growing. Well, that's the percent at which your money's growing, right? Your interest rate is how fast your money's growing as a percent. And so that's what we're going to multiply by, and I'm going to simplify that before I use it. Alright, so that simplifies to 335 e to the 0.06767 times time. Alright, now I'm going to plug in 0. Alright, so when you plug in 0, it's actually that number out front. Alright, that's the initial rate of change, right? Just like in this problem, that 5,000 is the initial amount. Well, that number in front of this e is the initial rate of change. So that's how fast it's growing as soon as you put your money in. Right, again, units. Answer the question, how fast? So the investment is growing at a rate, at a speed of $335 per year, right? It's a yearly rate of growth. All right, so that's the units on it, dollars per year, it's growing. All right, D, how fast was the investment growing in 5 years? And so D is, again, how fast, which means derivative, in 5 years. So you're going to take the derivative equation, so this equation we found over here, and plug 5 into it. So I'm going to plug 5 into that 335e to our interest rate times time. All right, comes out 468.31. It should make sense. It's going to have a bigger rate of growth because we've got more money in there, right? Every year that goes by, we're going to be growing faster because the more money we have, the faster my money will grow, right? Money makes money. And so it's bigger than when we started out. 5 years later, it's growing at a bigger rate. Again, don't leave it 468.31. Answer the question and put units on it. The investment is growing at a faster rate at a rate of dollars, so 468.31 dollars per year. All right, dollars per year is the units on that. All right, the last question. After how many years? So I'm going to erase this over here. I'm still going to leave my derivative because I know I'm going to use it. All right, so the last question, our last part of this question, E, part E, after how many years? So we want to know how many years. So we're looking for time. Will the investment be growing at a rate of $915 per year? And so it's giving me the rate of change, right? Which means it's giving me a future derivative amount. I know it should be in the future because 5 years at 600 or 468, so it should be significantly farther down the line, so much further than 5 years down the line. All right, so what you're going to take is you're going to take the derivative, set it equal to 915, and solve for time. All right, so my derivative was 335 e to our interest rate 0.67 times time equals the interest rate or the rate of change we're looking for, 915, and then you just solve that like we've been solving all the other equations. Divide by the initial rate of change. All right, so over here we're left with the e term. Here we're left with, and that might reduce again. You can reduce the fraction if you want to. I'm just going to leave it 915 divided by 335. Take the natural log of the e, take the natural log, forgot my n, of that side. And now we've got 0.067 times time equals the natural log of the 915 divided by 335. Last step, divide by the interest rate. Alright, so you're going to take this expression and plug it in your calculator as is. And so I'm going to write my answer over here. Alright, when you plug in the natural log of 115 divided by 335, it rounds nicely to 15 years. Alright, so t is approximately 15 units years. So in 15 years, it'll be growing by $915 per year. Alright, so the answer to E is 15. And it should make sense. It's quite a lot longer. It's 10 years after the 5-year period, which it was growing at that amount. Alright, so in 15 years is when it was growing at $915 per year. Alright, so again, shorter assignment this time. This one was just sort of a special case, a money example of instantaneous rate of change. The last type of application we're going to look for in terms of exponential, we'll do logarithmic, a couple of examples of logarithm. But the last type of exponential, which will be the next set of notes we'll set it up, will be the logistics model, where we've got limited growth instead of uninhibited. Right, so again, the previous cases were uninhibited, we could grow indefinitely. The next set of notes we're going to look at what's called logistics models and limited growth, meaning we can't grow forever. There's going to be a limit to it. And we'll talk about that more, in the next set. Alright, we're going to wrap that up there.